Hello everyone, I am Shimanta Shaha from Verification Lab at University of California, Santa Barbara. Today I am going to talk about our paper Preach, a heuristic for probabilistic reachability analysis to identify hard to reach statements. The other co-authors of this paper are Mara Downing, Dr. Tegan Brennan, and Dr. Teffin Bolton. Preach is a heuristic for probabilistic reachability analysis to identify hard to reach statements. Given a program and a target statement, Preach identifies if the target statement is hard to reach or easy to reach. Let's consider this program from software verification competition benchmark. There is an assertion statement in the program. Let's say someone wants to run a random testing tool to test this program. Now the question that Preach can answer is the assertion statement hard to reach using that random testing tool? Or the question that Preach can answer, what is the likelihood of reaching the assertion statement if we run a random testing tool? To identify hard to reach statements in the program, Preach does a probabilistic reachability analysis. Given the program and a target statement, one can do some kind of probabilistic reachability analysis and then identify if a target statement in the program is easy to reach or hard to reach. Existing techniques that can be used for probabilistic reachability analysis are probabilistic symbolic execution and statistical symbolic execution. But the issues with existing symbolic execution-based techniques are that there can be exponentially increasing number of program paths. Also, the linear increase in path constraint size can lead to exponential cost of symbolic execution-based analysis. And this complexity increases further if someone is using a model counted constraint solver for probabilistic analysis. In Preach, we develop a heuristic for probabilistic reachability analysis to identify hard to reach statements. And the heuristic can be helpful to mitigate the problem with existing symbolic execution-based techniques. Given the program and the target statement, Preach computes a reachability probability to the target statement, and given a threshold, using the reachability probability computed by Preach, one can identify if the target statement is hard to reach or easy to reach for a random testing tool. Whereas traditional symbolic execution-based techniques need to deal with path constraints, Preach deals with branch constraints only, which can help to reduce exponential analysis cost of symbolic execution-based technique to polynomial time analysis cost. In Preach, we develop a heuristic-based technique for probabilistic reachability analysis that trades off accuracy for scalability. Here is the workflow for Preach. Given the program and the target statement, Preach constructs a discrete time Markov chain from the program, and then using a probabilistic model checking tool, Preach computes reachability probability. And then using the reachability probability and based on a predefined threshold, it identifies the target statement as either easy to reach or hard to reach. Now the question here to ask is how Preach can construct the discrete time Markov chain from the program and the target statement. This is the workflow how Preach can construct the discrete time Markov chain from the program and the target statement. From the program, first Preach extracts the control flow graph, and then Preach performs dependency analysis from the test input marked by the user. And based on this dependency analysis, it can identify which branches in the program and in the control flow graph are test input dependent. On the other side, Preach also performs branch selectivity analysis. And together, using the control flow graph extraction and dependency analysis and branch selectivity, Preach can construct the discrete time Markov chain from the program and the target statement. At the very first step, Preach takes input as the program, and then it extracts the control flow graph from the program. Then Preach performs dependency analysis on the control flow graph. The branches in the program which are not test input dependent are not considered in the control flow graph as a branch. Then Preach computes branch selectivity. Let's first explain what is branch selectivity. Let's consider this program where input parameter to the test function is the test input. We also consider that the input variable is a 32-bit signed integer. So there are 2 to the power 32 possible values, and our assumption is that the inputs are uniformly distributed. First, the branch condition is extracted from the program. In line 2, the branch condition is input is equal to 0. Once we have this branch condition, it is transformed to a SMT leaf formula, and a branch constraint is constructed. Now that we have this branch constraint, we make a query to a model counting constraint solver, and the model counting constraint solver can provide us with the count of the satisfying solution to the branch condition. Now that we have this model counting number, we can divide it by the domain size, which is in this case 2 to the power 32, and then compute the branch selectivity. Let's consider this branch at line 2. We see that the probability of taking this then branch is 1 by 2 to the power 32, which is very low, and we can say that this particular branch is selective. On the other hand, the branch condition at line 4, the probability of taking this then branch is 0.5. This branch is not selective because lots of input can pass through this branch condition. Once we have this branch selectivity computed, we also apply some refinement. Branch selectivity based on branch model counting only cannot catch variable updates. We collect refinement conditions using abstract interpretation. If you consider the branch condition at line 4, it is y is greater than 0. That means all the positive values for y. And the branch selectivity we can compute is 0.5. But this is not actually representing the number of input that can pass through this branch condition at line 4. After applying abstract interpretation based analysis, we can compute new refined branch conditions, which is y is greater than 0 and y is less than 0. These two branch conditions contradicts each other, and as a result, we get a new refined branch selectivity, which is 0.0. That means this particular branch is very selective, and as a result, the assertion statement is hard to reach. Once we have this control flow graph and the branch selectivity based analysis, we can put this probability as edge weight in the control flow graph and construct the discrete time Markov chain. Now that we have constructed the discrete time Markov chain from the control flow graph of the program using branch selectivity analysis, how can we compute reachability probability using this discrete time Markov chain? What we can do, we can transform this discrete time Markov chain to a DTMC model in Prism. Prism is a probabilistic model checker which takes as a discrete time Markov chain model and a query. One can write this query in different form. In this case, we construct a PCTL query from the given target node in the control flow graph. The query asks what is the probability that target node in DTMC is reached eventually. And once we send this DTMC model and the PCTL query to Prism, Prism can compute the reachability probability. For this running example, Prism computes the reachability probability as very low. And as a result, Preach identifies the target statement in this program as hard to reach. We developed our technique of heuristic-based probabilistic reachability analysis to identify hard to reach statement for Java programs. When we use simply model counting based branch selectivity, we call this tool as Preach. Preach has two other variations where one can use interval analysis or a box domain for branch selectivity refinement. This is called as Preach I. Also, one can use a relational analysis or a polyhedral domain to refine the branch selectivity, and this particular technique is named as Preach P. We experimentally evaluated our tool Preach for SDCOM benchmarks, which is software verification competition benchmarks, and we also analyzed some case studies from Apache Commons Lang project and some DARPA benchmarks. Our tool Preach is available at Zenodo, and also one can run Preach using Docker from the Docker Hub link that we provided here. Our tool is functional, reusable, and available. In Preach, we collect the ground truth using a generator-based random fuzzer based on JQueue and JEST. We run this generator-based random fuzzer for 1 hour. And if the generator-based random fuzzer fails to generate input that can reach the statement, we identify the statement as hard to reach. Else, we say that the statement is easy to reach. For the running example from software verification competition benchmark, the random fuzzer generates 4 million inputs and none of them can reach the assertion. As a result, the ground truth is hard to reach for this particular statement. From Preach side, we also predict that the statement is hard to reach, which means Preach can correctly identify a statement as hard to reach if the program is tested using a random testing tool like a generator-based random fuzzer. We assess Preach on software verification competition benchmarks, and we achieved very high accuracy, precision, and recall. As you can see, the accuracy for Preach for the software verification competition benchmark is 95.8, the precision is 95.1, and the recall is 90.2. We compared Preach to probabilistic symbolic execution for the purpose of identifying hard to reach program statements. We see that for lower search depth, like 10, probabilistic symbolic execution computes a probability which is not accurate probability but an approximation. But the approximation that is computed by probabilistic symbolic execution is even worse than a heuristic-based technique like Preach. On the other hand, if we increase the search depth for probabilistic symbolic execution to 1000, lots of programs time out. That means the probabilistic symbolic execution times out for lots of programs in the software verification competition benchmark if we run it for 1 hour. Overall, we see that both Preach I and Preach P have better precision, recall, and accuracy compared to probabilistic symbolic execution. Now that we see that Preach has very high precision, recall, and accuracy compared to probabilistic symbolic execution for programs in general, we compare the analysis time between these two tools. We see that for lower search depth, the probabilistic symbolic execution is very fast, and the analysis time we have using Preach is comparable to the analysis type of probabilistic symbolic execution. But on the other hand, when the search depth for probabilistic symbolic execution is increased, it is orders of magnitude slower than heuristic-based technique Preach. In general, we find that Preach is orders of magnitude faster for programs in general compared to probabilistic symbolic execution. Next, we compare Preach to statistical symbolic execution technique. Statistical symbolic execution has better precision, recall, and accuracy compared to probabilistic symbolic execution, but not compared to Preach P. We see that from our experimental evaluation, recall and accuracy for statistical symbolic execution drops with increased search depth. This is the same scenario we have observed when you compare it with probabilistic symbolic execution. We also compared analysis time for Preach P and statistical symbolic execution, and we find that Preach P is orders of magnitude faster than any of the sampling techniques in statistical symbolic execution. We developed a technique called Preach based on heuristic for probabilistic reachability analysis to identify hard to reach statements. And this technique and tool can be used for other tasks in software engineering, like quantitative program analysis, probabilistic analysis of software, guiding hybrid testing strategies, improving random testing, and fuzzing efficiency. Let's go through this program. This program is taken from a fuzzing paper where they use it as motivational example for hybrid fuzzing. As you can see, there is a complex check at line 8. And random testing tools and fuzzers cannot go through this complex check. As a result, fuzzers like AFL, AFL Fast, and Fair Fuzz get stuck in block C. One can use hybrid fuzzers technique like driller, QSIM, which invokes symbolic execution every time fuzzer is stuck. Now, symbolic execution based technique can easily generate an input by solving these constraints of this complex check, and it gets back to fuzzer with this particular input. And once the fuzzer has this new input, it keeps mutating and makes progress in fuzzing. Now the question here is how much time is wasted before realizing that the fuzzer is stuck? Or the question here to ask is how to decide when to invoke symbolic execution in a hybrid fuzzing technique. One can simply prioritize paths for symbolic execution and then divide the task between fuzzer and the symbolic execution. We can use Preach to probabilistically prioritize this path for symbolic execution. That is, we can identify which paths in the program are hard to explore for a random testing tool or fuzzer, and then we can send this path to a symbolic execution based tool, and symbolic execution can solve this program path and then provide these inputs to the fuzzer, and then fuzzer can mutate these inputs and make progress to test the program and achieve better coverage. I would like to thank you all for listening to this talk. I have presented a technique called Preach, which can be used for probabilistic reachability analysis. And in this paper, we used this technique to identify hard to reach program statements if you are trying to test this program using a random testing tool. And the technique we developed here can be used for quantitative program analysis and probabilistic analysis of software, or even to guide hybrid testing techniques. Thank you.